Okay, so we're going to talk about digital logic circuits. Okay. We can use truth tables to determine if a logic statement is true or false. But computers are built out of the same type of logic statements. Okay. So we can use them to understand basic computer programming as well. Okay. In our translation from logic statements to computers, a true statement will turn into a 1 and a false will turn into a 0. And what do we mean by this? Traditionally, a true statement of 1 is that the switch is turned on. A false statement of 0 is that it is turned off. And so everything is about, is the switch on or off? We are going to use 3 types of what are called logic gates. So our first type of logic gate is a NOT gate. It is usually drawn in this manner, where P is the input that goes into the NOT gate and R is the output that comes out. This is equivalent to the logic statement that is negation. So, if we had a truth table for negation, where we're calling not P R, P can either be true or false, and the not will switch the logic value to false and true. For our NOT gate, we would write this as follows. We have the input of P and the output of R. P can either be 1 or 0, and the NOT gate switches those values to 0 and 1. Our second type of gate is an AND gate. And this works the same as a logical AND statement. So how do we draw this? First of all, there are 2 inputs to an AND gate. We may call them P and Q. Here is our AND gate, and it outputs an R. This works just the same as a logical AND. I'll remind you of the truth table for that. Okay. We had 2 inputs, P and Q, and then the output, P and Q, which we are here calling R. So all possible combinations of P and Q's truth gives the following outcomes for P and Q. If we rewrite this for the logic gate, truths turn to 1 and falses turn to 0, and it is identical. Okay, there is a third type of gate. That is, of course, an OR gate. Once again, there are going to be 2 inputs. You can call them P and Q. I have a little bit more trouble drawing this one personally. Okay. Can't remember if I wrote AND in the middle. I did. So you'll notice we tend to still write the OR and not inside the gate. It helps if you're not that great at drawing. Okay. So 2 inputs and an output. Okay. This works just like a traditional OR statement. So if I have its truth table, it will translate exactly for the OR logic gate. All right, so far we're basically just giving things new names. What is most interesting to us, though, is when we have more than one gate in play. Traditionally, we call this a sequential circuit. Gates will be in sequence. So, as an example of one, 2 inputs of P and Q that first hit an OR gate. Something comes out of the OR gate, and it goes into a NOT gate. and then we get an output. So we could trace what happens to this. For instance, if P equals 1 and Q equals 1, let us trace what happens to it. Okay. So here I'm plugging in 1 and 1 to an OR. Okay. An OR of 1 and 1 outputs another 1. That goes to the NOT gate, which flips it to a 0, and that becomes our output. Okay. So I'm literally tracing my values through. We can do this for all possible inputs and outputs. Where inputs consist of P and Q and output consist of R. All right, so we've already done the first one. Input 2 ones, we outputted a 0. Okay. Let's try the next one. So if I input 1, 0 to an OR gate, I still get 1, which is negated to 0. If I input 0, 1 to an OR gate, I still get 1, which is negated to 0. If I input 0, 0 to an OR gate, I get 0, which is negated to 1. This is called an input-output table for this circuit. Okay. All right, so we're going to practice making another input-output table with a more complicated circuit. Okay. I'm still going to have 2 inputs, P and Q. P, however, is first going to hit a NOT gate. Okay. And then something interesting is going to happen. So we haven't seen this yet, but it is possible that an output can go to more than one place. So, okay, after coming out of the NOT gate, whatever comes out of P is also going to come down here, and with Q, enter an AND gate. Okay. Then whatever comes of that will go to a NOT gate. Okay. And that, which goes into this OR with the above line. Now I want to point out something. This dark circle here says that the sequence split there. So whatever comes out of the NOT follows both directions here. Okay. If I don't put a dark circle like that, it implies that the lines are on top of each other but not actually touching. And it was just drawn that way for convenience of drawing it. We're going to see some of that later. But again, when I have this dark circle, it means that the value goes in 2 different directions. Okay. All right, so let us make an input and output table. Okay. Once again, I have my 4 possible combinations of P and Q. It is going to be a little bit harder for me to trace them. Okay. All right, so if P and Q are 1, okay, tracing the P line, 1 comes into the NOT gate, so 0 comes out. That sends a 0 to here and a 0 to here along both branches. The 1 from the Q comes to here. All right, so I have a 0 and a 1 going into an AND gate, which produces a 0. That goes into the NOT gate, which produces a 1. So now I have a 0 and 1 going into an OR gate, which produces an output of 1. Okay. And we have to do this for all 4 possibilities. So if I'm putting in a 1 and a 0, the NOT gate switches that to 0. Okay. Sorry, that was supposed to be a 0. The AND gate of a 0 and a 0 is a 0, and the NOT switches it to 1. OR of 0 and 1 is 1. Okay. 0 and 1. NOT gate switches to 1, which tracks to both of these locations. This one is still here. 1 and 1 into an AND gate produce a 1, which the NOT turns into a 0, and then sends along. Now I have a 1 and a 0 going into an OR gate. That is a 1. Okay. All right, one more option, 0 and 0. Okay, NOT switches it to 1, which gets sent to both of these locations. Okay, 1 and 0 hit an AND gate and produce 0, which a NOT sends to 1. So now I have a 1 and 1 going into an OR gate, which produces a 1. Okay. All right. You see, this can get very, very complicated very, very quickly. Okay. Again, remember these places where things cross. If they have that solid dot, it means the value gets sent in 2 different places, but it was the same value each time. Okay. You see why I liked the color coding. Okay. And then you just have to trace in sequential order. It is always moving from left to right. It might go up or down, but is always going generally from left to right. All right. It is also possible to go the other way around. That is, I can give you an input-output table and ask you to produce a circuit for it. This is a little bit harder. Okay. So, let me give you an input-output table. With 3 inputs, I'm going to need 8 possible ways to combine them. Okay. All right, now there is a trick to it. First of all, there are many circuits that could have this input-output table. Okay, we are simply going to produce 1, and we like this procedure because it always gets us an answer. It may not be the cleanest answer. First, we are going to look for those rows, okay, that correspond to an output of S equals 1. Okay. Here, here, and here. Okay. All right, now I'm going to create a Boolean expression for each of those rows. That is, an expression using P, Q's, R's, and the logical connectives of AND, OR, and NOT. Okay. So, looking at my inputs, on each one, what is the input that gives that result? So, to get a 1, 1, 1, to only be able to only produce a 1, I need P and Q and R. Okay. So this came from row 1. Row 3, okay, we have a 0 in the middle. Okay. So it'll be P and not Q and R. Okay. Essentially, I'm ANDing all of them. If it was a 1, I include it. If it was a 0, I not it. So our last row is not P and not Q and not R. Okay. Now together, these are the only 3 ways that I can get a 1 value in my output. Okay. So I'm going to take them and put an OR in between. Okay. Again, I'll remind you, I did not say this would be the cleanest way of getting an answer, just that I was going to produce an answer. Okay. All right, but I wanted to draw a circuit. This is where things get fun, and I'm going to need a lot of room, so I'm going to take that result and copy it over here. Okay. Whew. All right. This is going to get a little complicated. First of all, I have 3 inputs, P, Q, and R. Okay. Next, I'm actually going to build this from right to left. So S is my only output. And the very last step which is the last thing we do in the order of operations, are those ORs. So the very last thing that it is going to hit is going to be an OR gate. Okay. That has 3 inputs. Okay. 1 for each of my parenthetical expressions. Okay. All right, so let us go after them one at a time. Okay. I need something that will compute P and Q and R. Okay. So obviously we're going to have an AND gate. And what is going to go into the AND? Well, P, Q, R. Okay. And they just go straight into that AND gate. Now the first statement was easiest because there were no nots. Okay. For the second statement, okay, I'm also going to have an AND gate. Okay. And what is going to go into that AND gate? Well, P is, and R, and not Q. Okay. So, to get P into here, I'm going to put a little breakpoint on the P line and drag it down to that AND gate. To get R into there, I'm going to put a little breakpoint on the R line and drag it down to the AND gate. Now I left room in the middle because I need to get not Q in there. So I'm going to put a little breakpoint in the Q line, but before I put it into the AND gate, I will send it through a NOT gate. Okay. All right, I have one more expression to do. Okay. Again, the last thing that it hits is an AND gate. Okay. This time, there are 3 things that go into it, and they all need to go through a NOT gate first. Okay. So, I'm going to take P, that I'd already broken off from, and drop it further down to here and send it through a NOT gate. Okay. I'm going to take Q that I've broken off, drag it down to here, send it through a NOT gate. Okay. I'm going to take R that I had broken off, drag it down further, send it to a NOT gate. Okay. So, reading right to left, the last thing they all go through is an OR. There are 3 parenthetical ANDs within that. This AND contains P, Q, and R in direct line. This AND contains P, not Q, and R. And this one contains not P and not Q and not R. And of course, this matches our results from the original table. Okay. So that gives us a circuit that would have produced that table. Again, it is not the only one, especially if you rearrange things spatially. If I had drawn PQR in different orders, if I had broken them off in slightly different places, you can get different circuits with the same table. But this is one answer.